Hello everyone, and thank you for letting me speak at this event. So on the first slide, it gives the title of the talk, and it's basically going to be about the role of open source software in UK academic or scientific high performance computing. So throughout the talk, I'll probably refer to high-performance computing just as HPC. So onto the first slide, which gives, well, before going on to the first slide, I guess I should say a little bit more about myself and my colleague Neil, who, as Jeremy mentioned, are based at the Hartree Centre, which is located at the Science and Technology Facilities Council's Daresbury laboratory. Well, my own background is mainly in helping users to port, optimise and tune their applications for HPC. And in doing that, I've been kind of exposed to quite a few legacy Fortran codes, C codes, and the I guess heavily computational type codes. My colleague Neil, his background is more on the data science, mainly the non-traditional type HPC that we're now seeing, such as big data and data analytics. So I'm more on the traditional, I like to call it traditional HPC side, whereas Neil is more of the up-and-coming HPC. But my side is geared towards the scientific aspect of HPC. So onto the first slide, which gives the overview of what I'm going to talk about this evening. Basically, I'll go into more detail about what the Science and Technology Facilities, or STFC, is, where both Neil and myself work, and where the Hartree Centre and the Scientific Computing Department fall into that. Then I'll talk about where and what the main high-performance computing centres are in the UK, and a little bit about what they provide. Then I'll talk about what we're going to look at in terms of what are the scientific codes or applications to use in HPC within the UK. And also an important aspect in HPC, as with any scientific computing application, is the efficiency of the code when it's running on the system. So I'll talk more about that. And of course, as I go through these different topics, I'll bring in the open source aspect, which is very important. It'll become more apparent as I go through the role of open source within HPC. Moving on, I'll talk about, again, the open source influence on how codes are implemented and open source compilers, tools, applications, programming interfaces, and other methodology which is used for parallelism. They're both very, very important and widely used in HPC, obviously. And furthermore, tools that are used to aid code development. I guess tools like profilers that can identify bottlenecks and performance issues within applications, and debugging tools. I'll also talk about one other important aspect of HPC, which is quite important, the use of external libraries. Those are applications which have been developed and tuned by others so that they can be reused within HPC applications. So that in effect, the user doesn't have to reinvent the wheel if they want to use a particular routine or whatever. And finally, I'll end off by talking about three quite well-used scientific applications in the UK. So on to the next slide, please, Jeremy. So to mention a little bit more about what STFC is, or the Science and Technology Facilities Council. It's one of the UK's publicly funded research councils. So that means that STFC gets the main source of funding from the UK Business Innovation and Skills Department. And that's similar in effect to other research councils like EPSRC or NERC or the BBSRC. But I guess the STFC is a little bit larger than those other research councils, but they all come under RC UK, the Research Councils UK. In total, they're responsible for supporting and promoting research within the UK, and the STFC in particular is very interested in innovation and skills development. However, the STFC concentrate more on the particle physics, nuclear physics, and astronomy areas. STFC has quite a large number of members of staff, and it also has, in addition to those members of staff, around 900 or so PhD students, which are sponsored throughout a distributed network of UK and international or European universities. So STFC does fund quite a lot of research through the funding it itself receives from the UK Research Council's body. And STFC has two main sites, one of which is located at the Rutherford Appleton Lab in Harwell, which is just outside Oxford. And the one where I'm based is up north at Daresbury Laboratory in Cheshire, which is just quite close to Warrington, for those that are familiar with the area. So on to the next slide, I'll say a little bit more about what the main departments which in STFC which concentrate on the scientific computing aspect. One of those is the Scientific Computing Department, or SCD, and essentially that has in total probably about 30 years or more experience in developing, designing, implementing scientific software, mainly within the UK, but some of the applications that have been developed at STFC in SCD are used internationally as well. The SCD also provides support for the UK's collaborative computational project, of which there are about currently 14 or so. Now these are essentially consortiums who join together to share knowledge and ideas in a particular scientific area to help with knowledge transfer and promote the science within that area. And they're determined via the Research Council's UK funding mechanism, and they change from time to time, but as I mentioned, at the moment there are about 14 or so, and they are all supported, or their applications are supported in the Scientific Computing Department at STFC. That includes code development, part of porting the applications to new hardwares, and also software support if users need to know how to use a particular application and so forth. Now the Hartree Centre is situated within the Scientific Computing Department, but it's slightly different in that its aim is to have a collaborative effect on getting industry interested in using science more as well. So they work the Hartree Centre works in collaboration with Scientific Computing Department. And to a certain extent, they're much the same. So for all intents and purposes, they can be viewed the same. So on to the next slide, please, Jeremy. So I'll now talk a little bit about the UK high-performance computing centres, where the actual hardware is located within the UK. And I'll start off by talking a little bit about what's known as the regional high-performance computing centres. Then I'll talk more about the slightly larger ones, which are located Wales, Ireland, and Scotland. So the regional high-performance computing centres have been in existence around 2.5 years or so, after an initial capital investment from the Engineering and Physical Sciences Research Council, which, as I mentioned before, is part of the RCUK setup, which also includes the STFC, where I'm from. And they set these up, these regional high-performance computing centres, to really give or provide a scale that existed between the local cluster university-based resource and the national HPC service, which is currently Archer. In terms of what constitutes a regional size cluster, then we're talking about 10,000 cores or less. And nationally, they're termed Tier 2 resources, with Tier 1 being the national level service, currently Archer. However, in Europe, they seem to knock one off that number, so a Tier 0 would be Archer, and a Tier 1 would be a regional centre. So, on to the next slide. In addition to the regional HPC centres, which are located, there is one of those located in Scotland, just outside Strathclyde, but most of those are located within England. So other HPC centres are HPC Wales, which again has been in existence around 2 to 3 years. It has 2 large hubs, but they're located in the south of Wales, and again it's of Tier 2 size. And basically the aim of HPC Wales is to support not just the academic supercomputing, but to promote high-performance supercomputing within businesses as well. In addition to HPC Wales, we've got the Ireland's iCheck High Performance Computing Centre. That's been in existence quite a bit longer than the others, and they do have very strong links with other European centres and hubs. So, as well as them being located in Dublin with a decent-sized computer system there, they've also got good access to quite a lot of kit over Europe as well. So on to the next slide. I'll talk now about the larger high-performance computing centres, which are based, one of which is where I'm from, at STFC in Daresbury, the Hartree Centre. And the other I'll talk about in a minute is based in Edinburgh. So just to talk a little bit about the Hartree Centre, it's been going now just over 1.5 years, and it was initiated following quite a large government investment. Its aim is to be complementary to the other UK large supercomputer, and it's to provide both academic high-performance computing resource and resource for high-performance computing to businesses. In terms of what hardware is available at the Hartree Centre, we've got quite a range of large, well, we've got one large machine which has over 100,000 cores. That's an IBM machine based on the Power 7 architecture, for those that are familiar with that. And it also has quite a range of Tier 2 machines, each with roughly around 10,000 or so cores. Now, those are mainly based on the traditional sort of Intel Xeon architectures that we find in our desktops and laptops at home. There are also other machines as well based on novel architectures or low power systems, FPGA machines and energy efficient machines such as those based on, well, there's one arriving soon based on the new ARM 64-bit ARM v8 architecture, and that will be a reasonable size cluster as well. But that's not in service yet. So the other national academic supercomputer is Archer, which is a Cray XE30, and that uses the traditional Intel Xeon architecture. I think it's an Ivy Bridge for server chip, probably 24 cores. Now Archer is located at the Edinburgh Parallel Computing Centre, also known as EPCC, which is located within the University of Edinburgh. EPCC itself started in 1990, so it's been going quite a long time, and it is recognised as one of Europe's leading supercomputing centres. And it is the host of Archer, which is the national, well, the UK's national supercomputer. So I'll now go on to the next slide and talk about Archer. So Archer is the successor of Hector, which you may have heard of, which was the previous national academic HPC resource. And Archer followed quite a large investment from the government. It provides capability resource to run large simulations that kind of have a justification for performance computing. It's not really intended for jobs or applications that can only use a few cores. Really, to get the benefit from Archer, it's better if your application can scale to a reasonably large number of cores. Otherwise, the application may be better placed on what we've called a Tier 2 type resource at the regional centres. But the aim of Archer is to enable researchers to study problems that will have a very large impact on science. And of course, in terms of performance, it is now the UK's most powerful computer. I think that was probably announced last week at Supercomputing, but due to a recent upgrade which has taken Archer to over, well 118,000 cores, it's now capable of quite an impressive 2 petaflop peak performance. So, on to the next slide. I'll give a breakdown now of what the scientific application areas are for UK academic high-performance computing. And basically, most of quite a lot of the simulations involve materials chemistry and chemistry-type simulations. There are also a large number of the environmental type, which by that I would consider sort of weather research forecasting, aerosol modelling and atmospheric modelling type applications as well. Similarly, engineering type, computational fluid dynamics, structural mechanics, they also make up quite a reasonable percentage of applications. And then at the other end, there is a small amount of research going into porting, optimizing and tuning other applications. So I'll now move on to talk more about the applications themselves, and so on to the next slide, please, Jeremy. And I'll also bring in the open source aspect, because I'm sure you're all very eager to hear about that. So most, you may not be surprised to hear that the majority of applications that are used in high performance computing in the UK are mostly open source. Or if they're not open source, one can usually get them by sending a request to the custodian of the application. And usually that custodian is willing to accept changes. If, for example, if you use the code and you find there's a bug in it, or you make a suggestion, usually they're quite welcoming at accepting the changes or suggestions. So applications that are running on HPC are usually well supported within their own communities, and it's very rare to find any community that isn't willing to share knowledge, ideas, or any experiences gained in running their code on a new platform or how to use it. There are a few applications, however, that are commercially based, but these are mainly in engineering type areas, such as finite element modelling, structural modelling. Those kind of applications do require a license. However, they're not that widely used on the larger systems, such as Archer and the larger tier 1 resources. 100,000 cores at the Hartree Centre, because in general it's quite difficult to get that type of application scaling up to that level or number of cores due to the underlying algorithms that are used within the code. So on to the next slide. I'll talk about what makes efficiency in HPC applications in terms of the considerations needed to get a code or application running efficiently on a HPC system. So when a code is developed or designed for high performance computing, such as a computational fluid dynamics code or whatever, if you take an algorithm which does finite difference and then you code it in Fortran or C, and then you decide to bring in parallelism with MPI or OpenMP, then it's very important that as you go through the development cycle, you take care that parts of the code are always being optimized to make efficient utilization of whatever is there in terms of the hardware. Now for HPC, not only do you have the CPU, but you've also, not only do you have the CPU and memory, you've also got to take more consideration in terms of what the I/O is doing, and if you're doing any inter-CPU communications, what the interconnect is doing, because these become of major importance in HPC, because if they're not working efficiently, then CPU cycles are getting burnt and they're extremely costly. To get time on a HPC system, it does cost. In one way or another, either the time is allocated through a notional mechanism, or it has to be allocated in terms of monetary cost. And for every core hour or notional allocation unit on a high-performance computing system, this has to be paid for. So obviously, if you have an application running on there, you want to get it to run as quickly as possible and to use as least CPU cycles as possible to be economic. Therefore, code performance is of utmost importance. Now, how is this achieved? Well, applications or codes are always run from a compiled object code, which is it needs to be optimized as much as possible for the particular hardware in question. So obviously the first step is to choose which compiler you're going to use, Fortran or C, whether it's Fortran or C code, and then as the source code is being compiled, use the compiler as much as possible to give messages as to what it's doing with the code, look for vectorization, loop unrolling, whether it's fusing or splitting loops, etc., how much cache usage you're getting, but take full advantage of what the compiler's doing is very important. In addition to the compiler, or what the compiler is optimizing, then it's also important to look at afterwards to look at the actual performance with the profiler, and at which point you can look at what's happening with the communications, I/O, and memory or cache utilization. So on to the next slide, please, Jeremy. So as I mentioned earlier, code is usually implemented in Fortran or C. I think on the national services, roughly about 80 or 90% of the applications are Fortran based. There are quite a few C codes as well, but generally there are a very small number of applications that use C++. There are some that do, and they tend to be written in that way because of the abstraction available with C++ that may be very suitable for the particular mathematical algorithm that's being coded up. But in general, Fortran is the choice for getting the best performance. For parallelism, MPI is usually the choice for for enabling communications between the distributed data. OpenMP is usually the choice for shared memory parallelism. Also, what's becoming more widely used as we're getting heterogeneous HPC systems, though I haven't mentioned this earlier, but there are some, at the regional centres, they do have heterogeneous HPC machines, which consist of both the traditional x86 Intel type chips, together with usually NVIDIA-based CUDA accelerators. And what this means is that for certain applications, they can take advantage of very high levels of threaded-based parallelism using CUDA or the other well-known GPU programming language, OpenCL. However, for the national services, it's mainly MPI and OpenMP because they're not heterogeneous. So, in addition to the traditional, I guess, parallelism approaches or methodologies, there are also now there's a few codes that do use Fortran and Unified Parallel C. There are other languages as well becoming more widespread, but traditionally we're seeing Fortran. So to talk more about compilers, on the next slide please, Jeremy. One of the popular compilers which is available, as far as I know, on all of the HPC systems is the GNU compiler. And in fact, this is often the compiler of choice in HPC. Well, for many reasons, but one reason is that it's good at checking whether your code adheres to Fortran standards, for example, in Fortran. And it's also usually very good at getting a decent optimization without changing much from the default level of optimization. I've mentioned on the slide that sometimes this is beaten by vendor compilers, and this is true often because they tend to be very good at obviously optimizing or producing compilers that are good at optimizing for the particular hardware platform that you're using. So if you're using something like the GNU compiler, then it can do the same usually, and usually you can get the same level of optimization and performance, but it will take a bit more work than it would with the vendor's version. It may take some code rearrangement, some loop reordering, or bringing things out of loops, etc. But you'll still be able to eventually you should be able to get the same performance eventually, but it could take a lot more work to do that. And also, I guess from my own experience, I tend to think that the GNU compiler is good at ensuring that you do keep to the Fortran standards quite closely. Sometimes other compilers will let you get away with things that you perhaps shouldn't. So yeah, the GNU compiler is definitely widely used in HPC. So away from compilers, we'll move on to the next slide, please, Jeremy, and talk about how we implement parallelism within these applications. So generally, for the distributed data, well, when you design a HPC application, you need to decide how the data is going to be distributed if you're using the distributed data decomposition. And for communication between the distributed areas of data, you have to use some kind of message passing protocol. And for that, the most common choice is MPI. Now there is an open source version of MPI, MPICH, and again that is widely used. However, as with the compilers, sometimes the vendor implementations are better optimized for the interconnect. Now, in HPC this is important because one of the most costly areas usually in the I guess in the performance of the code is whether it's doing any internode communications. And ultimately, if you have a version of MPI that's optimized for the interconnect, then you're going to get better performance. So unfortunately, sometimes it's not best to use the open source MPICH in this scenario, and the better approach is to use the vendor's implementation. But it may not be such a big issue if you're not using many cores, or if you're on, say, a system with a less advanced interconnect. So in addition to MPI, we have the shared memory parallelism, which is usually implemented with OpenMP, and again that's available in GCCC by just specifying the -f OpenMP flag, and of course with that you can use all the directives to use shared memory parallelism. So just quickly moving on to the tools for code development that are often very efficient and useful to use. The open source tools which are widely used in HPC for version control, we've got SVN. Also, Git is often used to provide version control. The point about parallel debugging is that most of the tools for that are not open source. However, there are a few, namely the Open Performance Analysis Toolkit. That's very good at profiling your application for performance by using tracing analysis. So that may add an overhead when you run the code, but it's well worth it in the end because it enables you to see how much, for example, whether the code's making good use of the cache, whether the inter-process communications are causing a bottleneck or things like that. Now, for non-parallel debugging, there are quite a few open source applications available for that, the widely known gprof, GDB, LLDB, and Valgrind. These are okay and they're very good to use for HPC because it is important to optimize an application for a single process, not just having it run in parallel. And a lot of applications seem to overlook this, surprisingly. So on to the next slide, please, Jeremy, thanks. So the libraries and applications programming interfaces are available for HPC. They're critical because it enables the user to reuse already developed code which has been optimized or tuned for good performance on HPC. So it saves a lot of repetition of work. And there are, I guess, one of the most widely used or well-known open source versions of those is the PETC library. And that provides it's basically a library of data structures, routines, solvers for partial differential equations that are going to, I guess the ones that are going to end up solving sparse linear systems. And PETC is widely used throughout, so that's a very heavily used application. And similarly, OpenFOAM as well. It's important to use the optimized linear algebra routines in HPC because again they're usually tuned for best performance. So before finishing off, I'll now move on to three widely used. Before moving on to the applications, just one more slide on the libraries and APIs. As I mentioned before, I/O operations in HPC are very expensive. Efficient I/O is therefore very important. This is something that one perhaps doesn't have to consider when writing an application for a desktop or a laptop. But I/O in HPC is quite complicated. There are a lot of things that could be tuned. Essentially, if you have a distributed application, then each CPU is going to be writing data to a file store. Therefore, it's efficient that the file store, that this is done in an efficient way so that the file store can handle that. And there are different layers within the file store for enabling this, but the user has to take advantage of them. So one library that enables some level of abstraction from the difficulties in implementing efficient parallel I/O is the ADIOS, Adaptable I/O system. And that again is open source and very widely used throughout the world, really. So in addition to I/O, I mean, there are other I/O libraries as well, like NetCDF and HDF5. Those enable a self-descripting approach to the data structures in question, and that can lead to more efficient I/O, because I guess the one thing that you don't want to be doing is writing I/O in ASCII. It's more efficient to use binary, obviously, but then it's also quite difficult to check or debug if the I/O is done in binary. So therefore, libraries and tools to help with that are very useful. So the other expense in HPC is communication, and that consists of mainly point-to-point or global type communication. And the point-to-point isn't usually too bad, because what we're doing there is just passing data between neighbouring CPUs, or even two CPUs that are not closely connected. But the problem generally happens when there are what are termed global communications or collective communications, and in those cases, every single CPU that's being used has to communicate, and sometimes it has to communicate with each other. So we're getting a very complicated graph of communication, and that is incredibly expensive. So to do that efficiently is very important. And again, there are commands there are calls in MPI to do this, but as I mentioned earlier, they have to be checked that they're optimized for the particular hardware that you're using. And furthermore, sometimes it can be difficult to use them because they can it can become very complicated. So there have been libraries written to enable the user to do that more easily, one of which is the one I've mentioned there, the 2DComp and FFT library. And what that does is basically enable you, if you have an application that has to use fast Fourier transform, FFTs, then you will need to do global communications, because you'll be transforming from a spectral space to a real space and so forth. And you may have different dimensional Fourier transforms, and to do that it can get quite complicated. So the 2DComp and FFT library enables the user to look at the communication and the handling of that at a very high level. So it makes it much easier for them to do in an efficient and an easy way. So now, I guess on to the last three or so slides, and I'll talk about three different widely used applications in HPC. The first of which is CP2K, and that is basically it's I think it's an ab initio or atomistic and molecular type simulations package, and it generally contains quite a lot of functionality. So it is one of the most widely used codes on, I guess, on the national service. I think it could be the fourth or so most widely used code. And I did mention earlier that roughly 40% of the applications in UK National Academic Scientific HPC are materials chemistry based. So this is one of those codes. But to give you an idea of what it consists of, well, it's quite a few lines of Fortran. It's been in development since, I guess it's been in development around 7 or more years, and it's recently undergone quite a bit of further software development. For that, we're talking about possibly 5 or so person years effort or more to add OpenMP with the existing MPI to make it more efficient for the many core type architectures that we've seen becoming more prevalent over the last few years. And recently it's also been developed for accelerators by adding CUDA to parts to enable parts of the simulation to be deployed to GPUs for the heterogeneous HPC type architectures. Now, I'm guessing that to be able to use CUDA, it's using the Fortran-C interoperability features of Fortran 2008, I guess. Though I haven't looked into that. But with all those features, it is scalable now to over 65,000 cores, and that's quite good performance for that type of code. So for anyone that's interested, there is a web page, it's widely supported, and it's open source. So any developments or so forth, that they all get back to the users. It's a well-supported community behind the code, and it's very successful in getting support for further development. So the next application is I guess it's an international well-known toolbox called OpenFOAM, which is the Open Field Operation and Manipulation Computational Fluid Dynamics Toolbox. It's been in existence for just over 10 years, so that's been in different forms. It's an open source package, a very large package. It consists of anything from financial modelling to the more widely used features which are in computational fluid dynamics. It's interesting from one aspect in that it's written in C++ with NPI, so it's not the traditional Fortran-C developed code. But it scales pretty well for certain areas of its functionality, and it is very widely used. And again, it's very large, over 1 million lines of code. It's well supported, and there are several forums and contributors to this open source package. So on to the final one. Sprint is actually, I guess it's a bit different to the other applications in that it's to aid statistical computation with high performance computing. What it does, it provides an interface to the open source statistical language known as R. That in itself is a widely used package which contains the standard statistical features. In general, quite a lot of the statistical functions are they're able to be deployed on high-performance computing in an embarrassingly parallel fashion, so that they essentially don't require very many inter-process communication. They can be done separately. Then, following the completion of the calculation, the result can be collected and determined on one single CPU. But in general, Sprint is useful to bring high-performance computing to the statistical users in a friendly manner. And it's been very successful in encouraging a lot of the bioinformatics community in that respect. And as you can see, it's very useful in enabling new science. So it's well supported, and it's another open source package that's recently been developed further and continues to be developed. So finally, just to summarise, I'd just like to say that for those of you that perhaps didn't know, high-performance computing is very active within the UK scientific community. It does enable new science. A lot of the facilities of the high-performance computing resources, they're extremely useful in enabling experiments that would not otherwise be possible in laboratory situations or experimental situations. Funding for academic high-performance computing kits, such as the hardware, is usually much greater than that provided for the software development or to develop applications that will run on that hardware. And that's quite an important point to note, really, in that it would be good if I guess if we could get more investment in software development. And that's really important because applications do need to be really efficient and optimised, and therefore software development for high performance computing is critical. And on that note, open source, or the open source aspect, is extremely useful for HPC software development, because how otherwise would users and developers share knowledge, share experience, and get developments back to the community in a timely manner. So overall, thank you very much for listening, and I hope you enjoyed it. If you have any questions, please ask.
Okay, thank you very much indeed, Phil. So while James is setting up, we'll take a couple of questions from Phil. Any questions? Yes.
Hello, Phil. This is Peter Crouch, the chairman of the Fortran Specialist Group. We're always we're always on the lookout for speakers to talk about successful and widespread applications of Fortran. We usually do that after our AGM, which is usually held in October. I was wondering if I could ask if you or your colleague would be willing to talk to us next October.
Certainly, that would be great. Thank you, Peter. Yes, I'll get back to you on that.
Yes, if you go to fortran.bcs.org, you'll see my details there.
Okay.
I'll make the link up because I've got email addresses for people. So.
Okay.
Yeah. Okay.
Right. Thank you.
Thanks.
Okay. One thing, I think, Phil, just for people, because we've got a mixture of, well, mostly industry people here, I suspect, rather than academia, something I only relatively recently became aware of. The sort of facilities that are provided at Hartree are actually available to business users, and indeed, the reason I know Phil is because of us jointly putting together a proposal. So Phil, if there are business users here who want to get involved, who think they've got an application that would benefit from access to national HPC facilities, what's the approach they should take?
They can contact, there is an email address, I really can't, I think it's probably helpdesk@hartree.ac.uk, but I can get that back to you, Jeremy.
Yes.
Or contact myself or Neil, and we can put them in contact with the business development guys. I can say that usually time on the machines is chargeable, but generally, you know, the business development guys negotiate that. Okay.
Right, well Phil, thank you very much indeed. You're welcome to stay on the line to listen, but since I think the next talk's probably quite visual, you might benefit from watching the video afterwards.
Okay, will do. Thanks, Jeremy.
Okay, thank you very much, Phil.
Thank you very much. Goodbye, everyone.
Bye.